lesson 9.5, solving parts of triangles. Our objective is that given two triangles, you'll be able to determine whether they are congruent and use that to find missing angle measures. Some quick vocab review. An equilateral triangle is one in which all the sides are congruent. An isosceles triangle is one in which at least two of the sides are congruent. The at least is really important here. An equilateral triangle has two sides that are congruent. It happens to have a third side that's also congruent. But what this means is that every equilateral triangle could also be called isosceles because at least two of the sides are congruent. Scaling is when none of the sides are congruent. All three sides have different lengths. An acute angled triangle, often just called an acute triangle, is one in which all the angles are acute. All three angles in this triangle are less than 90 degrees. A right angled triangle, or just a right triangle, is one in which one of the angles is a 90-degree angle. It can't be all three, because if we had three angles that were 90 degrees, they would not form a triangle. Same thing for, excuse me. Same thing for an obtuse triangle or an obtuse angled triangle. It's a triangle in which one of the angles is obtuse or greater than 90 degrees. All right, let's get into example 1. We have an equilateral triangle ABC, so all three sides are congruent. They have the same length. And if these are the measures of each side, one's x plus 9, another one's 3x minus 9, and another one is 2x, we can find x. We don't even need all of that information. I can just use AC and BC. We are told that AC is x plus 9. We don't know what x is yet, but we're going to find it. And BC is 3x minus 9. I have an equation, and you've seen lots of equations like this. We can get x by itself. So let's start by subtracting x from both sides. And while I'm at it, I'm going to add 9x to both sides. I kept the equation balanced. That is a legal math move. So when I combine my like terms, on the left side of the equal sign, I'll be left with 18. And on the right side of the equal sign, 3x minus x is 2x. We're almost done. 2 times some number x equals 18. That should leave us with x equals 9. And that's it. We're done. You could have solved it differently. You only needed to do one, but if you chose a different way, you might have chosen BC and AB. And you could set those two lengths equal to each other. If you set 3x minus 9 equal to 2x and solve it, you'll get the same answer, x is 9. You could have even used AC and AB. And if you solve that equation, you'll get the same thing, x is 9. Okay, try practice problem number 1 on your own. So using the same picture, we still have an equilateral triangle. Find y, and if you can, find z as well. Pause the video, try it on your own, and then come check your answers. Okay, hopefully you noticed that AC and BC are the only ones written in terms of y. So you got to use those ones to solve for y. Hopefully you found that y is 7. And then for the challenge, you can use the fact that y is 7 to tell me how long in units each side is. Plug in 7 in for y. 7 plus 3 is 10, or 2 times 7 is 14, minus 4 is 10. So we're talking about an equilateral triangle with 3 side lengths that are all equal to 10. In other words, you could plug in 7, you'll get 10 is equal to this third side here that's defined in terms of z. And when you solve for z, you'll get that z is 3. All right, here's some definitions for isosceles triangles. Remember, isosceles means two sides are the same length. In an isosceles triangle, those two sides are called legs. The two sides that are congruent are called legs. The third side, that doesn't have to be congruent to the other two, is called the base. And then the angle that's connecting the two legs, that's called the vertex angle. And then the other two angles are called base angles. And it just so happens that base angles of an isosceles triangle must be congruent. So we have a couple theorems. The isosceles triangle theorem says that if two sides of a triangle are congruent, then the base angles have to be congruent as well. The converse is also true, though. So you could start by knowing that the two angles are congruent, and that's enough to say that, well, if these two angles are congruent, these two sides must also be congruent. So if two angles are congruent, then the sides opposite the angles are also congruent. We also have a vertex angle bisector theorem. So the vertex angle, remember, is this one that is it's the connecting angle of the two legs of an isosceles triangle. And if we bisect, so the bisector of the vertex angle, this line segment that cuts the angle in half is called the bisector. It is also the perpendicular bisector of the base. So it's perpendicular to the base, crosses at 90 degrees, and it cuts the base in half. So AD is congruent to BD. Let's go to example 1. You have three things we could use. One of these theorems, or one of these three theorems. We are given the isosceles triangle DEF, and we're asked to find the measure of angle D. So, since this is an isosceles triangle, we know that the base angles must be congruent. So, angle D and angle E are both the angles across from the congruent line segments, the congruent sides. So those have to be congruent. Let's just call it X. It's X degrees. But if that's X degrees, then so is this. All we have left to do is remember that the three angles in a triangle add up to 180 degrees. So if I add X plus 133 plus X, or 133 plus X, that's going to be 180 degrees, because no matter which triangle we're working with, the three angles in that triangle have to add up to 180. We can combine our like terms. That's 2x. So 133 plus 2x equals 180. If I subtract 133 from both sides, 180 minus 133 should leave me with, was that 47? There we go. And then I can divide both sides by 2. We should be left with 23.5. So the measure of angle D, it was X, it's going to be 23.5 degrees. That's our answer. I think this is the most straightforward way to tackle this problem using the isosceles triangle theorem. However, you could have used the vertex angle bisector theorem. So I'm going to erase this picture in just a moment. So copy it down if you want, and then rewind if you need to. But here's the picture again. I'm gonna zoom in on this red part here. So we could have used the vertex angle bisector theorem. So if I bisect this angle, cut it in half into two angles of equal measure, the vertex angle bisector theorem tells me that this is a right angle and that these two sides are congruent. So I can actually just look at, say, this yellow triangle here. Because I bisected angle F, I know this angle is half of 133 degrees. So that would be, what, 66.5 degrees? This is 90. So I could find this angle. Well, actually, you know what? It asks us to find the measure of angle D. So let's actually look at this triangle here. But the idea is the same. This angle is going to be 66.5 degrees. It's half of 133. And this is a right angle. This is 90 degrees. So in the yellow triangle, we have 66.5 plus 90 plus x, the angle we're looking for, 66.5 plus 90 plus x, is 180. Again, you can combine your like terms. 66.5 plus 90 is 156.5. If you subtract 156.5 from both sides of this equation, you'll get the same answer, 23.5. All right. We have a corollary to the isosceles triangle theorem. A corollary is a small result that follows directly from a theorem. So remember, the isosceles triangle theorem said that if two sides are congruent, then the base angles are congruent. This is saying that in an equilateral triangle, all the angles are also congruent. The way you can reason that, the reason it's a corollary from the isosceles triangle theorem is that we know this is equilateral, but let's consider it to be isosceles. Then the isosceles triangle theorem says these angles are congruent. But we could think of it as an isosceles triangle this way, and then these two angles are congruent. And you end up with the result that all three angles have to be congruent. We have another corollary to the converse of the isosceles triangle theorem. If we use the converse of the isosceles triangle theorem, it says that, well, if you have two congruent angles, you're dealing with an isosceles triangle, but you could apply that to these two congruent angles, and then we could say that these two sides have to be congruent. And you end up with the result that all three sides have to be congruent, so an equiangular triangle must also be equilateral. All right, so in example 3, triangle DEF is equilateral. So this triangle here, triangle DEF, I'm just going to move it right here. DEF is equilateral, and it's asking us to find the measure of angle DFE. DFE, that's this angle right here. So really, we could just call that the measure of angle F, right? That's the vertex of the angle we're trying to find. But since this is an equilateral triangle, all three of these angles have to be the same number of degrees, have to be congruent. So they're all x degrees. So we can say the measure of angle D plus the measure of angle E plus the measure of angle F. That's the sum of the three angles in the triangle, so it's got to equal 180. But angle F, we're just calling it x degrees. Well, they're all x degrees then, right? Because it's equiangular. X plus x plus x, that's 3x. And if I divide both sides by 3, I should get x equals 60. So in other words, the measure of angle DFE, what we're trying to find, is 60 degrees. Okay. If FDE, the measure of angle FDE, FDE is 15x, excuse me, then find x. Well, this angle has to be 60 degrees, right? Because they're all 60 degrees to add to 180 and be congruent. That means 15x has to equal 60. Let's make a better 5 there. If I divide both sides by 15, I'll get that x is 4. All right, problem number 3. If the measure of angle DEG, I'm going to erase this part now. DEG EG. That's this angle here. If that is 8y minus 4, find y. Well, because EG is the angle bisector, in fact, these are already marked. So it's cutting angle DEF in half. So we have this 60-degree angle here at the top. That means each of these should be 30 because we cut the angle in half, right? So we say that 8y minus 4 has to equal the 30 because it's 30 degrees. And then solve that equation for y. We can add 4 to both sides to get 8y equals 34. And if we divide both sides by 8, we can reduce that fraction to find that y is 17/4. And that is the end of 9.5. I have a summary here. If you can classify a triangle by both their angles and their sides, for example, a triangle could be right and isosceles, how many different angle type side relationship combinations can you come up with? I started the list here, so you could have an acute equilateral triangle, an acute isosceles triangle, or an acute scalene triangle. And I drew a picture, just a sketch is fine. So continue this list on your own, and I will go over this with you in class. As always, ask a question at the end of the video, and I will see you all in class.